Good morning, friends. Can you hear me?
Good morning, sir. Yes, sir.
Yeah, good morning. Who is on hold? There is somebody with the name on hold. That's, that's funny. Okay, okay, friends, let's move on. Um, on Monday, we had started our discussions on the last topic, which is boiling and condensation. We started with condensation, and we said that condensation can be of two types. One is film condensation, the other is drop-wise condensation. Drop-wise condensation leads to better heat transfer because the liquid doesn't stick to the wall, to the condensing surface, and therefore does not introduce any additional thermal resistance. But to have drop-wise condensation, you need a surface which is non-wetting or hydrophobic. So therefore, you have to specially coat that surface because at least normally most of our surfaces have some degree of wetting. Okay. However, naturally occurring substances can be hydrophobic, and I gave you the example of water on a lotus leaf or many other leaves as well. That itself, but that in itself is a very interesting field of study. It is called the lotus effect or the petal effect, because the same way you would see that, with your kind permission, you would see that droplets of water actually settle on petals of flowers as if they are, like pearls. They shine like pearls. So because of that, so what I'm trying to say is, the point I'm trying to drive home is that the I mean there are naturally occurring surfaces that are hydrophobic, but artificially one of the very common ways of making a hydrophobic surface is having a coating of Teflon. And you have seen even in your plates, etc., if there is a coat of oil, the surface becomes hydrophobic. When we put oil or cream on our skin, it becomes hydrophobic, right? And then you have to put soap so that the oily whatever coating is gone. All right. Mm, After that, we went over and started doing some analysis. And again, we owe our allegiance to Wilhelm Nusselt, who came up with that his analysis of predicting that if you have a vertical plate and a saturated vapor condensing on that plate, what would be the rate of condensation and resultant heat transfer. Okay, so with that, let us continue from where we left off, and let me share my screen. Go here. So last class, this is where we stopped. We got an expression for the film thickness delta x, as well as the mass of fluid that is condensing per unit width, right? And this is what we saw. As you can see, if you know the liquid and vapor properties, especially thermal conductivity, viscosity, and density, and you know the latent heat of vaporization or condensation, which is HFG, then, and we know what is the temperature, we can find out the thickness of the liquid film as a function of the distance from the top. And similarly, what is the volume at, if I take a certain distance x, what is the flow rate of the condensate? Okay. Now, one thing, remember, one of Nusselt's assumptions was that inside the liquid film, the only mode of conduction is mode of heat transfer is conduction. Now, that is not correct, because, and we know that you have a fluid, and especially something like, let us say, liquid like a water or so, and that is flowing over a surface. We know there will be a velocity gradient, there will be a temperature gradient, and that is not going to be linear. There will be, it's a bulk movement of a fluid, so there will be convection effects, which Nusselt said it can be neglected. But we saw that that is not correct. So what, nothing to take away from Nusselt because he was the first one who came up with this. We all make assumptions when we are doing something new. And after that, we start relaxing those assumptions and making things more more correct, but more complicated as well. Now, what happened was after this, and this is also a name that we are going to hear quite a bit today, Professor Warren Rosenau from MIT. Rosenau did pioneering work in two-phase flows, particularly boiling, which we are going to discuss right after this. But what he did was here, he took Nusselt's analysis and he suggested an improvement. He said that in this expression for delta X, which you see here, okay, we need to include the thermal advection effects or convection effects, okay? To do that and improve, so to do that, he suggested a change in this expression, which we are going to see. So let us write this, an improvement to delta X was, proposed by Rosenau, okay? Warren Rosenau. He said, or what he wanted to do was include thermal advection effects. So what was his proposal? His proposal was to replace, and we'll not get into why he did this. Of course, he did some analysis and experiments, but what he said is you replace HFG by HFG prime. And what is HFG prime? HFG prime is HFG times 1 plus 0.68 times Jacob number. Okay, so one more non-dimensional term. This is Jacob number. And what is it? He says this is Cp of the liquid times Tsat minus Tw divided by HFG. Okay, Jacob number after Max Jacob, and another stalwart of heat transfer. And let me also tell you that there is an award called the Max Jacob Award, which is considered the highest recognition in the field of heat transfer. Okay, we don't give Nobel prizes in engineering, right? And but many a times it's loosely called Max Jacob Award is often called the Nobel Prize of Thermofluids Engineering. Okay. All right, so Jacob number. So therefore, what happens as a result? The changed expression for the film thickness therefore now becomes, everything is the same, 4KL mu L Tsat minus Tw times X divided by G rho L minus rho V times H prime Fg, and this whole thing to the power 1 by 4. So once again, friends, there is no requirement for remembering all this. To be honest, I also don't remember. Okay, I have a piece of paper in front of me which you cannot see, and I have these formulae written down there. Okay, so even after teaching this, I also don't remember, and that's by choice, because I never felt that there is a need to remember all of these. As long as I know how to solve it, how to use it, that's what is important. All right. Okay, don't sue me. I am on camera, being recorded. But let me be honest. Now, next thing is, what is the surface heat flux? We are, of course, these are important. What is the film thickness, etc.? Yeah, from academic interest point of view, it is there. But if you ask someone, if you're doing a practical design, you will be interested in how much is the heat transfer I'm getting by condensation. How much is the heat that is being transferred from the condensing fluid to the wall, to that cold wall? Is it getting hot? Right. So that is what is important from a practical heat transfer engineer's point of view. So let us now use all that. Q double prime W. We would define it as Hx Tsat minus Tw. Okay. And this we know that since Nusselt analysis involves or assumes that the only mode of conduction inside the film is conduction, I can also write it as KL Tw, Tsat minus Tw divided by delta x. Okay. So I can find out from here, especially from this expression, what is the rate of heat transfer at any point x. Sorry. It's a function of x. So what does this mean? This means that Hx is KL over delta x. Okay. So Hx is KL over delta x. We know the expression for delta x. Just before this, we wrote it down here. So you divide it and you will get this. Okay. So what do I get? Let us look at this expression and write down pi delta. So KL goes to the numerator. There is a KL in the denominator in delta, so that kind of partly cancels out. So essentially what you will have is G rho L minus rho V H prime Fg times, you have a KL and you have a KL in the denominator, and inside it is to the power 1/4. So therefore you get KL cubed divided by 4. The KL doesn't remain anymore. Mu L Tsat minus Tw times x. This whole thing to the power 1/4. Okay. So which means that Hx is proportional to x to the power minus 1/4. Because the film thickness grows as x to the power 1/4. That's it. So which means that if you know h bar over a distance L, if you calculate, you will get it's 4/3. It's exactly like natural convection, HL. Okay. So if you do all this 4/3 outside, then you get this HL. You take this expression for Hx and replace x by L. That is all fine. And then you take this 4 out, you get an expression like this, 0.943, and then you have G rho L minus rho V H prime Fg KL cubed. This 4 gets out, and you have mu L times Tsat minus Tw times L to the power 1 by 4. And no, this was H bar. Oh, yeah, okay. So now I can also express a Nusselt number, an average Nusselt number, which would be H bar L over KL, and that therefore becomes 0.943 times G rho L minus rho V H prime Fg L cubed divided by mu L KL Tsat minus Tw to the power 1 by 4. So this, my friend, is the expression for Nusselt number for heat transfer due to condensation over a vertical plate suspended in a vapor at saturation temperature. Okay, total heat transfer H bar L A Tsat minus Tw Q total. And what is A? A is W times L. And total condensation, mass of condensation or mass of condensate. You can of course integrate delta X, etc. But why do all that? You just do this. Okay. All right. So that kind of ends our analysis. Okay. So what I will do is you have taken this down. So I will now move on. I have made some very elementary slides here. So you will see all these finally. Refer to class notes for derivations. Okay. So this I will make it bold. Okay. And the rest you have all these expressions. Okay. As a ready reference. But remember, it is possible to derive all these from very fundamental principles. Okay. Okay, 822. Any questions from anyone? I know I have spoken quite a bit, but I think this is straightforward that way, the derivations, etc. If you had followed every step, you would understand how we did it. Okay. So what happens is I'm going to upload a problem sheet for boiling and condensation. So you will see that mostly it is again use of correlations. All right. Total heat transfer, which is exactly what I was telling. Now this was laminar film condensation. Okay. Now there's something called turbulent film condensation, where what happens is, there is it's no longer a laminar. You know that the outline of the film gets disturbed. It's a wavy pattern that forms. If the length is too long, that is what happens. Okay. So there are correlations. If you have to now find out the Reynolds number with respect to delta. Okay, with respect to delta, and from there you will get these relations. Okay. Now Reynolds number, how is the definition with respect to delta? Now you don't have an U, etc. So this is how the expression is. So this one is, I've just shown it here. I've also put the calculation procedure because delta you cannot determine, right? So there's iteration that is involved, which I've shown on the right hand side. But for now, let us ignore this. You keep it with you, and it is technically out of syllabus. Okay, so let us keep it here still, so that later on, if you are, let's say you're doing a project next year, you will at least know how to use it, what to do, etc. If the film condensation is no longer laminar. Okay, now this one is important. The condensation, remember at the beginning I said that, and we also saw here, right? I mean, as the length increases, the delta increases, and therefore your Nusselt number goes down, your heat transfer coefficient goes down, average Nusselt number goes down, that is. So therefore, what we said is, and that's why we had made a statement at the beginning, that it's better to use, preferable to use shorter plates or condensation over cylinders, right? Now what happens if you have condensation over a cylinder? So a liquid film is going to form as is shown here. Let me go to full screen. Okay, so a liquid film is going to form. This is you can think of it just like a plume in natural convection that we saw, but now it's falling down, and it's actually physically the liquid film. Okay, so here also the thickness of the film increases as you go along the azimuthal direction, right? I mean, can I have the laser pointer? Yeah, see, as you go over the azimuthal direction, the film thickness increases, and therefore your local heat transfer coefficient will go down. Okay, and then finally the film falls off as is shown here, like a sheet, liquid sheet. Okay, we have seen some of these, not condensation, but the same behavior is if you have, if you have a railing in your balcony, let's say, and it's raining hard. Okay, you will see that this raindrops fall on the surface and then they fall off in exactly in this pattern. It has to rain really hard, and the surface has to be waiting and all that. But we have seen such incidents, such physical phenomena. So for a single tube or sphere, the H bar, this is the expression. If you compare it with the expression for what the expression that we derived, which you probably have in front of you in your notes, the expression that we derived for vertical plate, you see the form is exactly the same. Is G rho L delta rho KL cube H prime FG in the denominator, in the numerator, and mu L delta T, and instead of X or L you have D. Correct? However, what changes is this coefficient that sits in front. For a vertical plate, if you go, we saw 0.943. If it's a cylinder or a tube, it's 0.729. If it's a sphere, it's 0.826. Okay, so this C coefficient changes, the coefficient that sits in front. Otherwise, the expression is very, very common. I mean, very, very similar for vertical plate to cylinder to sphere. Okay. Now, many a times, what happens is just a single tube may not be enough. Okay, and you have a bank of tubes. For example, we saw this, like shell and tube heat exchanger. Let us say it's a shell and tube heat exchanger and it's a condenser. There is phase change happening, correct? So the liquid, the vapor is going to condense over a bank of such tubes. Okay, so think about it. You have a bank of tubes like this. Okay, 1, 2, maybe 3, 4, n. Right? If it's film condensation, this is how it will happen. The film that is collected on the uppermost or topmost tube is going to fall on the next one. And there will be additional condensation on the second tube as well. And then, so therefore the film that comes down from the second tube will contain the condensate both on the first tube as well as the second tube, and so on. Okay, so this is how it works. Now, the condensate is falling in form of a film. If the surfaces are non-wetting, it can also form in the form of drops. So we are not going to consider that. For film condensation, which I'm showing it as C, this this picture, the one in the center, the average heat transfer coefficient, over the bank of tubes is given by this expression, which is on the right. As you can see, it is exactly identical to that of a single tube, except there is a capital N, which is the number of tubes you have. Okay, this is the average heat transfer coefficient over a bank of n tubes aligned vertically, right? So you have a capital N at the bottom. Clear? So what does it mean? It means that your H bar is proportional to n to the power minus 1/4. Which means if I have more number of tubes, my average heat transfer coefficient goes down. Okay? So if I ask you why, what would you say? Physically, why do you think? Is this correct? Why do you think this should happen? Anyone? Why should the heat transfer coefficient go down? Average heat transfer coefficient. Come on, someone should be able to answer. Nobody.
Because as we go down, the film thickness keeps increasing.
Film thickness keeps increasing. Yes, exactly. So the average heat transfer coefficient on the second tube is going to be lower than that of the first tube. The third tube is going to be even lower than the second tube, and so on. And if you take an average, this is what you get. And the reason is exactly what you said, is because the second tube onwards, the film thickness is higher and progressively higher. So therefore, and as we saw that the film acts as a thermal resistance, so therefore the heat transfer coefficient on subsequent tubes will be lower. Okay, on the nth tube will be lower than that of the n-1th tube. And if you take an average, this is what you get. However, please note the total heat transfer will be higher, right? Because the area of heat transfer, area across which heat transfer is taking place, is N times pi dl, isn't it? So it is proportional to N. Okay, so which means that Q is proportional to N to the power 3/4. Okay, what I'm trying to say is, if you add one tube, you are not going to double. Okay, if you had condensation of one cylinder and now you add a second cylinder, your heat transfer will not get doubled, but it will increase at a rate of N to the power 3/4, not N alone. Because while your area goes up linearly with number of cylinders, the heat transfer coefficient goes down as a factor of 1/4. Okay. Dropwise condensation, steam condensation on copper surfaces. Typically, H values are higher. Reliable correlations do not exist. This is one correlation that was given by Griffith for steam condensation on copper surfaces. And this is what he gave. And as you can see, this is absolutely empirical. And I don't know, I mean, whether how reliable this is. Okay. So let me write down and say no reliable correlations exist. All right. So that okay, this is just one last part. There is also something called film condensation during flow. Let us say you have a flow of vapor through a tube and the tube walls are cold. So there will be condensation on the tube wall and while it flows. So again, this is out of the syllabus, but you see it here, right? This is called film condensation during flow through a horizontal tube. Okay, this is not a static vapor. The vapor is actually flowing through a tube. So as you would expect that initially it will be vapor and then there will be a film, condensate film that will form on the inner walls of the tube. And if you look along the streamwise direction, the core, the vapor core will slowly reduce and this film is going to form on the walls. Okay, this is just for your, again, a slide that I've included because as again, as an IITian and somebody who has studied heat transfer in an IIT, you are supposed to know what is flow condensation. That's the reason. Okay, rest of it, all these correlations, etc., keep it handy with you, no point remembering, but you should be physically able to, if somebody asks you, you should be physically able to visualize and say, yeah, if I have a tube and the vapor is entering, yeah, condensation will start happening on the walls, and therefore initially there will be a film, the vapor will flow through the central core and the annulus will be the liquid film, and the liquid film thickness will slowly increase and probably you will reach a stage where the entire vapor has condensed and what comes out of the tube is completely liquid. Okay, that brings us to the end of our discussion on click to exit. Okay, I'm clicking to exit. Why aren't you exiting, man? Okay, my screen seems to have frozen, but I hope you can all hear me. Okay, good. So finally I'm back. So this was about condensation, completely about condensation. We have only scratched the surface or tip of the iceberg, whatever you call, but a very elementary discussion over 1.5 lectures. And just to give you a feel of what condensation is, okay? Some basic correlations for condensation over a vertical surface and over a cylinder, so that you can use, at least make some calculations and solve some problems. Okay, but more importantly is the physical understanding that is important. How the film forms. The film is actually a barrier to heat transfer from the vapor to the surface, so on and so forth. Any questions? Okay, let me just think about it. I'm not asking you to solve it right now. Remember at the beginning, I think beginning of the lecture, when I said that it is more desirable to have, shorter surfaces. Because as we saw that the heat transfer coefficient goes down. Just 1 minute, guys. Okay, what is happening? Okay, so I had said that many a times instead of having a vertical surface like this, it may be possible to just roll it in this manner, okay, and make it a cylinder. Okay, I think you got it, right? And this virtual background is creating some issues. Can I change it? Don't even know how it came up. Okay, I mean, I'll try that in the break. So, but let us say what I think you got it. I mean, I have a sheet and I now roll it in the form of a cylinder. Okay. Earlier, so what would you have an advantage? That's the question, right? So how would you solve it? See, for a flat plate, vertical plate, if you know the length, you can find out the total heat transfer, the average heat transfer coefficient, and which we have seen. It was exactly this expression that you are seeing on the left, and the coefficient was 0.943, right? And this D will become L. When you roll it in the form of a cylinder, then what happens, that initial L now becomes pi D. If this was my initial height, when I roll it, it becomes pi D. Okay. And the correlation that you have to use is exactly the same, except your D now becomes L by pi. And the coefficient instead of 0.943 becomes 0.729. Okay. So you can calculate that. So you have everything else actually remains the same. The coefficient for a flat plate, vertical plate was 0.943. And in this case, it will become 0.729 times pi to the power 1/4, whatever that is. And you can check and you can see that whether you will have an increase or decrease. Okay, so this is an example of a problem. All right. So that's condensation. We still have about 20 minutes left to this lecture. So let me move on and start the next topic, which is boiling. And this is also a very favorite topic of mine. Boiling is an it's a complex phenomenon, but a very interesting one as well. And something we have all experienced, right? I mean, pani to sab log ubale hai na? You also make tea. You have taken a saucepan and put water and put it on the stove. So therefore, boiling heat transfer is something very, very common. We have seen it. We use it every day in cooking. All right. So the question is, when does boiling occur? Okay. I think it's very well known to you. So I have put a definition over here. When heat is added to a liquid from a submerged solid surface, which is at a temperature higher than the saturation temperature of the liquid, it is usual for a part of the liquid to change phase and become vapor. And this change of phase is called boiling. We know this. But please look at it a little carefully, especially the underlined parts. Heat has to be added to a liquid, right? And this heated surface is a submerged, has to be submerged. The surface that is supplying the heat to the liquid has to be submerged inside the liquid. Then it is boiling. Okay. So one of the things, for example, is pool boiling. And that's what we are going to study here. Pool boiling is what you see in cooking and all. You have a liquid pool which you are heating, pool of liquid which you are heating. This pool of liquid can be inside your saucepan, inside your kadhai, whatever. So the heat transfer is through a heater plate at the bottom, which is shown here. Okay. Heat transfer can also be through immersed heating coils, like you have in your immersion heaters, or your tea kettles, electric tea kettles, right? So we have seen this. We have seen all this. Okay. Now, in the first case, let me also tell you that you may argue that the heater surface is actually the stove, which is outside, right? So it is not submerged in the liquid. But that is not correct. It is submerged in the liquid because for the pool of liquid, the heater source is the bottom surface. Or if it's a metallic container, even the side surfaces. Okay. So therefore, I mean, you may be supplying the heat through this through this stove, either whether it's gas, electric, whatever it is. But for this pool of liquid, it doesn't know what exists outside. It just sees that, oh man, I have a heated surface at the bottom, and I'm sitting on that. I'm resting on that. So over here, bubbles will start to form. It will start changing its phase from liquid to vapor. The vapor bubbles will form and rise up. So this is pool boiling, where the liquid pool is stationary. And then when you supply heat, the change of phase happens on the heater surface. You have formation of vapor bubbles, which detaches from the surface beyond a point and goes and rises up and then collapses at the surface. Okay. Now, similar to flow condensation that we just discussed, we also have flow boiling, where the liquid flows through a tube whose walls are heated. We have seen this in convection. But in convection, what happened was if it came as a liquid, it also left this tube as a liquid. There was no phase change. But let us say while the liquid heats up, right, m dot Cp delta T equals to Q double prime times the area, it reaches its boiling point. Then what happens? There cannot be any more sensible heating. After that, it starts to change into vapor. And what will come out of the exit is going to be either vapor or liquid, most commonly liquid plus vapor mixture at a certain quality. Okay? This is called flow boiling. And the liquid has to move through this tube. In order to make this liquid move, you need an external agency like a pump. Okay? Now for this class, we are going to be restricted to pool boiling only. Okay. So what I will introduce you right now in the next few minutes is a very classical concept in heat transfer, which is called the pool boiling curve. Okay. So you think about it, imagine that you are boiling liquid in a vessel. Okay. And slowly the temperature of the vessel at the bottom is rising. Okay. Now for boiling to happen, the temperature of the surface, heated surface, must be above the saturation temperature, which is the boiling point, which is what we call. All right. So what I'm plotting on the x-axis is actually what we call the surface superheat. So what is the temperature difference or temperature rise above the boiling point? That is the delta T. Okay. So now what happens is This is a log scale. Yeah, this is a log scale, as you can see. At the initial stages, when I have small degrees of superheat, like 5 degrees, low single digits, what happens is, even though the temperature next to the heated surface, the temperature of the surface is above the boiling point, boiling per se doesn't happen. What happens is natural convection. Okay, I've taken this plot from Incropera, so it says free convection. As you know, personally, I don't like that term, but it's okay. So you have natural convection. You have a temperature difference, you have a heated, and therefore convection currents are going to set up. All right. So natural convection, the heat flux, which is plotted on the y-axis, is not very high. This is, remember, this is water. Okay. So we are talking about like kilowatt per meter squared, which is not very high, by the way. Okay. Now, let us say I increase the temperature even further. So what will happen? We have all seen this. Initially, some small bubbles start appearing on the heater surface. Okay. These bubbles grow a little bit, okay, and then detach from the surface. Okay, there's a bubble departure diameter, we call that. We are not going to get into all those details. The bubbles will grow, and after attaining a certain size, it is going to get detached. Okay, the buoyancy forces will overcome the surface tension forces, and therefore it is going to detach. Okay, and as it detaches, it rises through the liquid pool, comes to the surface where it collapses. Okay, so that is how heat transfer is taking place. The liquid absorbs the heat from the heater source, right? Turns itself from liquid to vapor and continues to grow, so more vapor is forming. At a certain point, it cannot remain attached to the surface anymore. It detaches, and because of buoyancy forces, now it rises and comes to the surface, top surface, the free surface of the liquid pool, and collapses. We have all seen this. We have all seen this. Okay, so this phenomenon is called nucleation of these bubbles. Now, as I keep on increasing the temperature, the frequency, the number of places where these bubbles form will rise. The frequency of the bubbles, the frequency of occurrence and departure of the bubbles will rise. And as a result, as more and more bubbles form, grow, and detach, your heat transfer also goes up. Okay, and that is why you see over here there is a sharp rise in the overall heat transfer. The slope of this line, this is q double prime over delta t. So the slope is actually the heat transfer coefficient, and you can see here the heat transfer coefficient keeps increasing. Remember, this is log scale. Okay, even though this looks linear, but actually the heat transfer coefficients are very high, and you can see the heat transfer rates are also high. It is almost changing in orders of magnitude. Okay, finally what happens as these bubbles start forming, and there are more number of sites where these bubbles form, these bubbles are going to grow. Correct? As they grow, they may come close to each other and coalesce and form a bigger bubble. Okay, right, these bubbles may coalesce and form a bigger bubble on the heated surface and then grow further before it detaches. Now, as this starts happening, we have what is called the formation of a film on the heated surface. It's a film of vapor, and remember, this vapor has low conductivity, and it is going to act as a barrier to heat transfer, because this vapor is now preventing the liquid from coming in contact with the hot surface. So therefore the boiling phenomenon is restricted. Okay, so as a result, what happens next is, with further increase in temperature, okay, with further increase in temperature, the heat transfer actually starts coming down. It's very counterintuitive normally, right? I'm adding heat, but my heat transfer is, I'm increasing the temperature difference, but my heat transfer is coming down. Why? Because I have got into this regime which is called, I'm going into this regime where the boiling is, where this liquid film, or sorry, where this vapor film is forming on the heater surface. Okay. All right. So friends, this period where you have the formation of bubbles and then bigger bubbles, and then you have these bubbles, you know, this bubble, this occurring more vigorously, more bubbles coming and forming, growing, nucleating, growing, detaching, and coming up. So this whole regime is called the nucleate boiling regime. Earlier it was natural convection, then you have nucleate boiling. This is where you get the maximum heat transfer, slowly increasing heat transfer. But once the vapor film starts forming, you have a transition to what we call nucleate boiling to film boiling. During this phase, the temperature starts coming down. Sorry, the heat transfer rate starts coming down. Okay. So over here, as you can see, there's a maxima in the amount of heat that I can transfer, and it is called the critical heat flux. After critical heat flux, you have this transition to film boiling, where heat transfer gets retarded, and which is what we see by this downward curve. Okay. It comes down and then it reaches a point after which it again starts going up. Sorry. Okay. It again starts going up, and this is the film boiling regime. Why does it start going up? It's still a film. Why would it start going up? Because look at the temperature differences now. These things are happening at very high temperature differences. The boiling point itself is 100 degrees for water. Then it is 120 degrees of superheat, which is like 220 degrees. Under such temperatures, actually, the radiation effects also start becoming important. Okay, and that is why in film boiling, you again start to see a rise in temperature. But you have to really go to high temperatures for this, because the radiation effects become again significant compared to the heat transfer rate by radiation becomes comparable to that due to boiling. Okay, the lowest point is called the Leidenfrost point. Over here, the point D is called the Leidenfrost point, after the person who studied this quite a bit. Okay, I'll come back and give you an example of what is Leidenfrost point. Okay, I think let us stop here now, and when we come back, we will discuss this further. Okay, I have some pictures I want to show you. I don't know why my cursor is not coming, but I'll show that to you. All right, so let's take a break over here. Let me stop sharing. And when we come back, we will continue from where we left off. Okay. So let's take a 5-minute break.